Hi, it's Matt, and in this video we're going to talk about what linear operators are, and then we're going to work on proving if an operator is or isn't a linear operator. So first, let's talk about what a linear operator is. A linear operator will be an operator that satisfies this following property. So if we call a generic operator omega with the operator hat, and we apply it to a constant c1 times a function f, plus the constant c2 times the function g, that should be the same as if we have c1 times the operator applied to f, plus c2 times the operator applied to g. So what this essentially means is that we could distribute the operator into parentheses, and also we could pull a constant out, or in other words, a constant is unaffected by an operator, as we see as written out here. So now, how do we prove that an operator is linear or not? We're going to list a few steps and then work through some examples. So first, we're going to write the left-hand side of the linear operator property. So omega hat and then the c1f plus c2g. From there, we're going to plug in our given operator into the equation. And then we're going to use mathematical properties and identities to attempt to get it to the form C1 operator F plus C2 operator G, which you should recognize as the right-hand side of the equation on the previous slide. From there, if you are successfully able to rewrite it in that form, the operator is linear. If we can't write it in that form, the operator will not be linear. So let's do an example of this. The example we're going to use first is our operator is the derivative, or more specifically, the derivative with respect to x. So again, I'm just going to rewrite our linear criteria for us, and now we're going to rewrite the left-hand side. So our operator, C1f plus C2j. Next, our first step is that we're going to replace our operator, so our omega hat, with the given operator. So we're going to use the equation given and plug in our operator for the derivative. From there, we're now just going to use our mathematical properties we know of derivatives to try to get it to look like this. So one thing we know about derivatives is that the derivative of a sum is the sum of derivatives. So to speak, we could distribute the derivative into the parentheses to get the derivative of C1f plus the derivative of C2j. But another property we know of derivatives is that when we have a constant inside the derivative times a function, we could pull the constant out, as the constant does not affect the derivative in any way. So when we pull the constant out, we get c1 times the derivative of f plus c2 times the derivative of g. But this is great because if we look, this looks very much like what we have up here, just instead of a generic operator symbol, the omega, we have our derivative. So now using the equation again that we're given up here, that d dx is omega, we're going to replace our derivatives with omega again. So what we have found is that omega times c1f plus c2g is the same as c1 omega f plus c2 omega g. Since these were all equal signs and we didn't do anything, we didn't choose a particular function for f and g, we left them generic, we can safely say that the derivative is a linear operator. So in this case, omega, or our derivative, is linear. Let's try another example. So now let's try omega hat is equal to cosine of the function. So this operator will tell us to take the cosine of whatever inside of it. So just as before, we'll rewrite the linear criteria and then write the left-hand side. Now, what we're going to do is we're going to particularize, so we're going to rewrite omega as the cosine. So this is equal to the cosine of c1f plus c2j. So now let's think about what mathematically we could potentially do to simplify this. And one such thing is to use this property here, that cosine of a sum, so cosine of a plus b, is equal to cosine a cosine b minus sine a sine b. So what we'll do is we'll call c1f a, and we'll call c2g b, and we'll use this identity to get that omega C1F plus C2G is equal to cosine C1F times cosine C2G minus sine C1F times sine C2G. And from here, we know that there's nothing we're going to be able to do to turn these sines into cosines. So we're never going to be able to fully just rewrite it in terms of omega. So we could safely say that this does not equal C1 omega F plus C2 omega J. There's just no way we're going to get it in that form. So we could safely say that the take the cosine operator is not a linear operator. So now, here's one for you to try on your own. So is omega equals x plus 5 a linear operator? I'll give you 5 seconds to pause the video, and then we'll talk about the solution. Okay, so you should find that omega hat equals x plus 5 is a linear operator, as we see here. And the two main reasons that we can say it's a linear operator is once we plug in x plus 5, that's just a polynomial. And we know that polynomials satisfy the distributive property, so we can multiply it in. And again, since everything here is just scalar multiplication, we know that it doesn't matter what order we matter stuff in, so we could easily move the C1 and the C2 to the front. So that's why omega hat equals x plus 5 is linear. So here's another example for you to try on your own. Is the operator e to the ... a linear operator? And what I mean by e to the ... is that when we apply the operator to a function f of x, that's the same as an exponential to the power of whatever is inside the operator. So here, omega f of x is equal to e to the f of x. With that, I'll give you 5 seconds to pause, and then we'll talk about the solution. Okay, so you should have found that it is not a linear operator, because when we apply the operator to C1F plus C2G, that gives us e to the C1F plus C2G, but using the rules of exponentials, we know that that's equivalent to e to the C1F multiplied by e to the C2G. So we see here that we're going to end up with multiplication rather than addition. Once we lose that addition to multiplication, we're never going to be able to get that plus sign here. There's just no mathematical way. And since we can't get the left-hand side equals the right-hand side for our linear criteria, we know that here omega is not linear. That's all I have for today. Thank you so much for watching. Have a great day.